Hello, everyone. Uh, we are not going to have in-person class on Thursday, September 26th, because we have some potentially dangerous weather headed our way due to Hurricane Helene. So we are going to do a virtual lecture instead. So today we are going to cover sections 3.8 and the first bit of 3.9. And then we'll finish the last part of 3.9 on Tuesday in class. We should just have a little bit left. And then we should have time in class on Tuesday for you to ask any questions and to review for the exam 2. And then your exam 2 will be next week, Thursday. That is October 3rd. And it's going to cover everything from the combined sections 3.1 through 3.2 all the way up to section 3.9. All right, so because we're not finishing section 3.9 this week, what I'm going to do is sections 3.7 and 3.8 will stand to be due on Monday, that's September 30th at midnight, and I'm going to move the deadline for section 3.9 to Wednesday. That will be October 2nd at midnight. Okay, so without further ado, let's get into it. So before we jump into section 3.8, I wanted to do a little wrap up to section 3.7 with the chain rule. At the very end of class on Tuesday, we had talked about layering rules on rules, right? And so if you have a problem that has both a chain rule and a quotient rule, or both a quotient rule and a product rule, or a product rule and a chain rule. How do you decide what rules to do in which order and how to piece everything together? And the answer to that is going to be that you need to identify the structure of the problem, and that's going to tell you which rule to start with. And you are just going to start with that rule. You're going to follow your steps, and you're going to do your steps in order. And as you do the steps for that rule, the other rules will kind of show themselves as you do the derivatives for the parts that you need. So first thing that you have to do is identify the structure of the problem. Now, that's not always the easiest thing to do. So like for this problem here, which we saw in the section 3.7 in class at the very end, to figure out how to start this and what the structure of this problem is, if you can't tell, I want you to plug a number in. So let's say we wanted to plug in x equals 2. So if I plug in x equals 2, I'm going to replace x with 2 everywhere. Now, if you were to evaluate this and start figuring out what the answer should be, the very last operation that you do will tell you the structure of the problem. So if I were evaluating this, I would add inside my square root and I would get the square root of 3. I would add on the bottom and I would get 4. I would plug the square root of 3 into my calculator to get a number up there, and I would take whatever number I had up there divided by the number that I had down here. Division is the very last operation that I would do as I evaluate this thing. That tells you the structure of your problem. Division is the overall structure here, which means to do the derivative of this, you're going to start with the quotient rule, because ultimately that's how we take the derivative of something with a variable divided by something with a variable. But division tells you start with the quotient rule. Okay, so what about this one? If I were to, again, I don't, maybe it's a quotient rule because I definitely see a quotient in there. But I also see an inside function and an outside function. So maybe it's a chain rule. And maybe I'm feeling like I don't know which one to start with. So what I want you to do is think, okay, well, what if I would plug a 2 in? How would I simplify this? Okay, so to start simplifying this, I'm going to add on top in here and I'm going to get a 3. I'm going to subtract on the bottom down there and I'm going to get 1. And then I'm going to do this division inside to simplify there, and I'm going to do 3 divided by 1. That's 3. the very last operation that I do is this exponent. What that tells me is that I have stuff to the fourth power. It tells me that I have something inside a power of 4, right? And it's something inside and next to the fourth. That means you have an inside function and an outside function. That means that you're going to start with, I can't spell, the chain rule. Sorry, y'all. It is late and my brain is tired. Come on. Okay. It's a chain rule. There we go. And so that's what you would start with. And you would start by identifying your inside function and your outside function and following through there. Because again, once you identify that this up here is your quotient rule, the quotient rule says you're going to call the top either F or high, you're going to call the bottom G or low, and then you're going to follow your rules and you're going to do low D high minus high D low over low low, or you are going to do G times F prime minus F times G prime all over G squared. And so as you do those derivatives, as you do your F prime or D high, and as you do your G prime or D low, that's when you will find other rules hidden in there. And down here, when you do the chain rule, you're going to do what we did before. You're going to identify your outside function and call it F. You're going to identify your inside function and call it G. And then you're going to take the derivatives of each of those. And here is where you would identify if you have other rules hidden inside that chain rule, you will find them when you do the derivative of your parts. And then what if we had something like e to the 3x sine of 1 over x? What if this was my function? What's the structure of that problem? What rule would I do first to find the derivative of something that looks like that? Well, again, I'm not sure. So what I would do is take a 2 and plug it in for x anywhere I see it. And I'm going to see how I would start to evaluate this. First thing I would do is simplify in that exponent, and I would get e to the 6th. And then I have a sine of 1/2 over here. And then what I would do is I would put e to the 6th in my calculator, and I would get a number out of there. And I would put sine of 1/2 into my calculator, and I would get a number out there. And the very last operation that I would do would be to multiply those two numbers together. What that tells me is that the structure of this problem is something with x's in it times something with x's in it. To take the derivative of that, you're going to do a product rule. To do a product rule, you're going to call your first function f, you're going to call your second function g, and you're going to do f prime times g plus f times g prime. And when you do f prime and g prime inside that product rule, that's where you will find any other rules that are hidden in there. So find the structure of your problem. When things kind of get scary and you feel like, oh, I don't know where to start, plug a number in. The very last operation you do will tell you what to do. If multiplication is the last thing that you do for order of operations, you're going to start with the product rule. If division is the very last operation you're going to do, it's a quotient rule is what you're going to start with for your derivative. And if it is anything else, if it's a power, if it's taking the sign of something, that's going to tell you that you have an inside function and an outside function, and you're going to start with the chain rule. Okay. So hopefully that helps you with 3.7 and when things get kind of hard and scary so that you have a way forward. All right, so now we are going to rock into section 3.8. 3.8 is all about implicit differentiation. That sounds really scary, but it's not going to be too bad, I hope. Basically, this is going to rely very heavily on the chain rule. And what implicit differentiation means is it is how we take derivatives. Differentiation means a derivative, taking a derivative. And implicit means we are going to be taking derivatives of implicit functions. Now, an implicit function is a function that can't be written as y equals f of x. In our traditional function notation, we can get y equals and get it all by itself and have y equals a function with only x's in it. That's kind of our standard traditional explicitly defined function. But sometimes you won't be able to get y by itself. For example, take a look at this function. It kind of looks like I have y equals, but over here, this is not a function of just x. I have x's and y's in here. And I won't be able to get this y out of sign jail to be able to combine it with this y and solve for one y on one side with only x's on the other. There's no getting into or out of this sign. And even if I try to rewrite it with inverse trig functions, this y over here will be stuck in inverse sign jail and we won't be able to get to it. So sometimes we're going to have implicitly defined functions like this where we cannot get y equals with only x's on the other side. But we're still going to want to know the slopes on those functions. So to find the slopes, to find your derivatives, we need to use implicit differentiation. Okay, how does this work? Well, it's basically the chain rule. So we are going to assume that even though I can't get y equals a function of x, I'm going to assume that y is in fact a function of x's, right? I somehow, some way in the universe, y is some kind of function of x's. Even though I can't write it like that, there's still that understanding that y is some kind of function of x's. So how would I take the derivative of this? Well, the derivative over here, right, the derivative of this function, dy dx, is going to be the derivative of 3x squared. We know how to do that. The derivative of 3x squared is 6x minus. This is the square root of y. Now, technically, y is a function of x. So I have a function of x inside a square root. To do the derivative of this, I'm going to do a chain rule because technically I have a function inside a square root function. And so we're going to do the chain rule. I'm going to say, all right, I need to identify my outside function and I'm going to call it f. And I need to identify my inside function and I'm going to call it g. Now my inside function here is y, which is some kind of function of x. I just don't know what it looks like. And my outside function is going to be the square root of x, right? It's stuck inside a square root function. And so now I'm not going to panic. I'm going to follow through my chain rule process. I'm going to take the derivative of f and the derivative of g and the derivative of the square root of x. How do you do that? Yep, you're going to rewrite that as x to the 1/2, and then you're going to do the power rule. You're going to get 1/2 times x to the negative 1/2. And I'm going to do the derivative of y, which the derivative of y is dy dx. It's whatever the derivative of y with respect to x is. And so now I'm going to finish the chain rule. I'm going to take my g and I'm going to plug it into f prime. And so I'm going to have 1/2 times y to the negative 1/2 times g prime, which is dy dx. This is implicit differentiation. Notice that essentially what I did was I took the derivative of every piece of this function. And when I took the derivative of something with a y in it, like the square root of y, I took the derivative just like I did with x's. If I called this y to the 1/2, the derivative, if I applied derivative rules to that, it would be 1/2 times y to the negative 1/2, right? It's the same derivative rules, just with a y instead of an x. But technically it's not an x, it's a y, which is a function of x. So we have to do the chain rule and multiply by the derivative of that function with respect to x. This is implicit differentiation. But I'm not quite done because I'm still after the slope, right? I want to know what the slope is. And the slope is my derivative, which is this dy dx bit. So from here, we're going to try to get dy dx all by itself. And If you took a calculus class somewhere else before this, I always use dy dx when I do implicit differentiation. You might have seen the same process, but using y prime or f prime or something like that instead of dy dx. You're welcome to use that. But I really truly feel like this is one of the places where Leibniz notation shines, and it really helps us out a ton. Because when you write your derivative as dy dx, these are the things we're going to solve for. They stick out like a sore thumb, and you can't miss any. Sometimes when you have y's and y primes both floating around in the same function, it's real hard to tell them apart and to find all your derivatives. So dy dx makes it real easy to find all of them. And so I have to solve for dy dx. So what I'm going to do is put anything with a dy dx in it on one side and anything without a dy dx on the other side. So I've got a dy dx on both sides, but I have something without it on this side. So I'm going to move this to the other side by adding 1/2 y to the negative 1/2 times dy dx to both sides. And when I do that, on this side, I'm going to get dy dx plus 1/2 y to the negative 1/2 dy dx. On the other side, I'm going to have a 6x left. And notice everything over here now has a dy dx in it, which means I can factor it out. And when I factor it out, dy dx divided by itself is 1 plus 1/2 y to the negative 1 dy dx divided by dy dx is 1/2 y to the negative 1/2. And I still have that 6x over here. And now to get dy dx by itself, I'm just going to divide both sides by this 1 plus 1/2 y to the negative 1/2. I'm just going to divide that off of both sides. And what we get here is that dy dx, my slope, looks like 6x over 1 plus 1/2 y to the negative 1/2. I guess technically these parentheses aren't doing anything in the bottom, so if you don't want to write them, you don't have to write them. That's totally fine. This is my slope. That's what it looks like. And we found the slope of an implicitly defined function. This is implicit differentiation. Okay, so what were the steps here? How did we do this? The first thing that we did was we took the derivative of both sides of the equation. You might have parts of an equation on both sides of the equal sign now. You have to take the derivative of everything on both sides of the equation using all of our previous derivative rules. You're going to have to apply product rules when you have something with a variable times something with a variable. You got to apply quotient rules when you've got something with a variable divided by something with a variable. You got to apply chain rules when you have something with a variable inside a function. And you're going to basically apply all of your rules pretending like all of your variables are just an x. But if you take the derivative of something with a variable that's not just an x, after you apply your derivative rules and take the derivative just like normal, you have to multiply by the derivative of that variable with respect to x. So when we took the derivative of y with respect to x, we multiplied by dy dx. So anytime you take the derivative of something with a y in it, multiply by dy dx. If you take the derivative of something with a theta in it, after you take the derivative, applying your rules, pretending it was just an x, you're going to multiply by d theta dx, whatever your variable is. And then once you do the derivatives of everything in there and you have a bunch of dy dx's floating around, you have to solve for dy dx using algebra. And once you get dy dx by itself, you, my friend, have found your derivative function and you can find slopes. So a couple of notes here. When do you use this, right? You have to use implicit differentiation like this when you can't write your original function in the form y equals f of x. If you have functions with both x's and y's on both sides or all together mixed up, you have to use implicit differentiation to take the derivative. And now another note that I want to make, take a look at this derivative that we just found. What's different about this derivative than any other derivative that we've seen so far? Yeah, it has both x's and y's in it. That is new and different and weird and totally allowed with implicit differentiation. Your derivatives, your dy dx's or f prime of x's, can now contain both x and y. So basically what that means is that if I want to find the slope at a specific point, I'm going to have to plug both x's and y's into that formula. And when I plug both x's and y's into that formula, I'm going to get a number out, and that number is going to be the slope at that point that I just plugged in. But instead of just plugging in an x value, now you're going to have to plug in the whole ordered pair with both x's and y's. No big deal, it's still slope, and you're still going to plug in to your derivative to find slope. Okay, let's do this. Okay, I want to calculate dy dx implicitly for the equation of the unit circle x squared plus y squared equals 1. And then we need to find the slope of the line tangent to the unit circle at the point 1/2 negative root 3 over 2. Sorry, I'm running out of water. Okay, so you might say, well, this is not an implicitly defined function, right? I could solve for y here and get y by itself. I could subtract the x squared from both sides and get y squared equals 1 minus x squared. And then just take the square root of both sides, and you would get y equals the square root of 1 minus x squared. But the problem here is that when you take the square root of both sides, don't forget your plus and minus. What happens is, to include the entire um, graph, I guess, of this equation, you need to break it into two functions. This x squared plus y squared equals 1 is the unit circle. Pretend that's a circle. Use your imagination for me. And when we solve for y like this, we get a positive square root and a negative square root. The positive square root represents the half of the circle everywhere up here where y is positive. This is what the positive square root gives us, is the top part. And then the negative square root gives us this bottom part, right? Everywhere y is negative is down here. That is what the negative square root gives us. But the problem is I can't get the entire circle with one equation. I need two equations to get the whole thing. And the reason for that is because this is not a function when I include both pieces. In order to write this as a function in function notation, I need y equals a single function, but I can't do it. I have to have two separate functions that I kind of piece together to find the entire graph. So technically it looks like we can solve for y, but we can't encompass the entire circle with just one equation explicitly. So we're going to do this with the implicit equation like this, so we can get the entire circle with one equation. Okay, now I want the slope of the line tangent. That means I'm going to need the derivative, right? That's how we find slopes of tangent lines, is a derivative. So I need to find dy dx. To find dy dx with implicitly defined functions, I'm going to take the derivative of both sides of the equation, right? Every piece of the equation, and just apply the derivative rules. So let's take the derivative of the left side. I've got x squared plus y squared. They're separated by addition, so I'm going to do it piece by piece. What's the derivative of x squared? Yep, it's just 2x. No big deal. And then I'm going to add to that the derivative of y squared. What's the derivative of y squared? Yeah, it's 2y. We're just going to apply our derivative rules to that. But I took the derivative of something with a y in it, so I'm going to multiply that by dy dx because I took the derivative of something with a y in it. And now here's the weirdo part. We now have to take the derivative of the other side as well. Literally everything in here. So what's the derivative of 1? It's 0 because it's all by itself. Okay, so now here's my derivative. We are in derivative land. Um, but I want to find the slope, right? I want to find dy dx. So we have to solve for it now. And again, Leibniz notation shines here. This sticks out like a sore thumb, and I can find the thing that I'm trying to solve for. I want to get that completely by itself. So to do that, I'm going to move this 2x to the other side to get the dy dx by itself on one side. So I'm going to have 2y times dy dx equals negative 2x. And then I'm going to divide by 2y to get the dy dx by itself. And I'm going to have negative 2x over 2y. These 2's are going to cancel, and I'm just going to get negative x over y, right? Because let me switch colors. These 2's cancel. Okay, so that's my derivative. This is my slope function. This tells me how to find the slope at any point on my original equation. Except now I have to find an x and a y to be able to find the slope. And so now if I want the slope at this point, then I'm going to take my derivative, my dy dx, and I'm going to plug in this point into it. And so anywhere I see an x, I'm going to put a 1/2 in. Anywhere I see a y, I'm going to put a negative 3/2 in. And so now I'm going to plug it in here. So I'm going to get negative x, which is 1/2, divided by y, which is negative root 3 over 2. How do I do negative 1/2 divided by negative root 3 over 2? You're going to keep change flip. So you're going to keep the negative 1/2. You're going to change this division to multiplication, and you're going to make your brain flip that bottom one. And you can, I'm going to have a negative times a negative. That's going to give me a positive. You can multiply straight across, and you'll get 2 over 2 root 3. These 2's will cancel, and you're going to get 1 over root 3. You don't have to rationalize for me. I really don't care if there are square roots in a denominator. Achieve is not going to make you rationalize. So this is going to be great for both me and Achieve. If your brain is programmed to rationalize, you can multiply top and bottom by the square root of 3, and you'll find that that rationalizes to the square root of 3 over 3. Either one of those works. Now, what does that mean exactly? So again, my original equation was the unit circle. Pretend, use your imagination, pretend that's a circle for me. And we just found the slope at this point, 1/2 negative root 3 over 2. So we're here at 1/2 negative root 3 over 2, right? Here's my point. And what we found was that the slope of the tangent line there, which looks something like this, the slope of that line is 1 over root 3. If you plug that into your calculator, you'll find it's a little bit smaller than 1. But that looks like a line with a slope that's in the vicinity of 1. So that looks legit to me. I feel really good about that. And hopefully you can see what that means. We're still just plugging our point into our derivative to find slope, but now we just need to plug both x and y in to find the slope instead of just x. Okay, so let's keep practicing. What if I ask you to find dy dx for this function, 4x squared plus xy equals y to the third plus 7? All right, this is an implicitly defined function, right? I'm not telling you to use implicit differentiation here. I just tell you to find the derivative, but you've got both x's and y's floating around together. So that tells you implicit differentiation. So you're going to start taking the derivative of everything in here piece by piece on both sides. So we're going to start on the left, and we'll do everything separated by addition and pieces. So we'll start with the derivative of 4x squared, and the derivative of 4x squared is, yep, 8x. And then we're going to add to that, what's the derivative of xy? How do you take the derivative of x times y? This is x times y. I have something with a variable times something with a variable. That tells me I have to do the product rule to take the derivative of this. Okay, so to do the product rule, my first function f is going to be this x. My second function g is going to be this y. And to do the product rule, I'm going to do the derivative of my first function. What's the derivative of x? It's 1 times the second function as is. My second function is y, plus my first function as is. My first function as is x, times the derivative of my second function. The derivative of y is, yep, whatever the derivative of dy dx is. Or you can think about the derivative of y being 1, and then you have to multiply by the dy dx because it's not an x, it's a y. So if your brain likes 1 dy dx, go ahead and put that in. Okay, so this is the product rule, and we had to do it because we have a variable times a variable. And notice this y did not have a dy dx in it. The reason for that was because this was the second function as is. I did not take a derivative of something with a y in it, so I don't need a dy dx there. But over here, I did take the derivative of y, which is why the dy dx is there. Okay, so we are in the middle of our implicit differentiation. We've done the derivative of everything. Oops, sorry. We've done the derivative of everything over here. And so now I have to do the derivative of everything over here. What's the derivative of y to the third? Well, the derivative of y to the third is 3y squared. And we have to multiply by dy dx because that's a y, not an x. Plus, what's the derivative of 7? Yep, it's 0. Okay, so now we've taken the derivative of everything in our equation here. And so once we take the derivative of everything, we now have to solve for dy dx. And again, I love Leibniz notation because these kind of jump out at you so you can see all of them. And so your goal here is to put anything with a dy dx in it on one side, anything without a dy dx on the other. And I see that I've got a couple things without a dy dx on this side. So I'm going to go ahead and move this over here. And I'm going to do that by subtracting x times dy dx from both sides. So now when I do that, I've got 8x plus y left over here. And on the other side, I'm going to have 3y squared dy dx minus x dy dx. And now everything on my right side has a dy dx in it, so I can factor it out. I'm going to have dy dx times, when I take it out, I'm going to have a 3y squared minus x. I still have this 8x plus y over here. And so now to get dy dx by itself, I'm going to divide this thing off. So 8x plus y over 3y squared minus x. That is my dy dx. That's my derivative function. Implicit differentiation. All right. So again, just our usual derivative rules. We're just adding in the step to multiply by dy dx when you take the derivative of something that's not an x. All right, number 3. What on earth is this asking you for? Yep, it's your second derivative. We can do repeated derivatives with implicit differentiation the same way that we could do it with the others. So we're not going to panic. We're going to find our second derivative. How do you find a second derivative? You first find your first derivative, right? And then whatever you get out of that, you take the derivative of that again. We can do that implicitly. We're going to take the first derivative with implicit differentiation. We're going to solve for dy dx, and whatever we get out of that, we're going to apply implicit differentiation rules to that. So here we go. Let's find our first derivative of this thing. Both sides. If we do the derivative of the left, we're going to do everything separated by addition in pieces. So what's the derivative of x? It's 1. Plus, what's the derivative of y? It's also 1, but we took the derivative of y, so we have to multiply 1 by dy dx. If your brain likes 1 dy dx, put it in there. Equals What's the derivative of e to the negative y? Well, you might be tempted to say that the derivative of e to the negative y is e to the negative y. But the thing about that is that that only works if you have just an x up there. We don't have just an x up there. We have a negative variable up there. You have e to the stuff, right? That's not just an x, that's stuff. You need a chain rule for this. So we're not going to panic. We're going to do the chain rule. We're going to say, what's our outside function? We're going to call that f. We're going to say, what's our inside function? And we're going to call that g. And we're just going to do our chain rule. What function is inside something else? Yep, it's negative y. That's the thing inside our function. And so what's that function inside of? Inside the function e to the x. And so now that we've identified our inside and our outside function, now we're going to do the derivatives of our pieces. The derivative of e to the x, that is in fact just e to the x because that's our basic rule. And the derivative of negative y is negative 1 times dy dx. So now we're going to complete our chain rule. We're going to plug g into f prime. And so we're going to get e to the, instead of x, I'm plugging my negative y in there, times g prime of x, which is negative 1 times dy dx. I'm just going to write that as negative dy dx. Okay, now we've done the derivative of the right side with the chain rule. And love Leibniz notation. I have a dy dx. They stick out like sore thumbs. And so now I'm going to put anything with a dy dx in it on one side. So I'm going to move that over by subtracting it from both sides. And I'm just going to have a 1 left over here. And on this side, I'm going to have my original side here. I'm going to move this negative out front so that my brain doesn't turn that into subtraction. And then I'm going to subtract this dy dx that I subtracted from both sides. And again, I have a dy dx on everything over here, so I'm going to factor it out. And I'm going to get negative e to the negative y minus 1. I still have that 1 over here. And now to get dy dx by itself, we're going to divide this thing off of both sides. So 1 over negative e to the negative y minus 1. That's our dy dx. That's our first derivative. But we're not done. We were asked for the second derivative. Okay, so how we now have to take the derivative of this. How do we take the derivative of this? Well, as is, I see a quotient rule, right? I've got something divided by something with x's in it. And so I could actually do this in its current form with the quotient rule. I've got something divided by something else. That tells me I could do this with the quotient rule. Or if you want to do it a different way, your brain might see that, oh, I have just, this is just a 1, right? So technically I should be able to do this without the quotient rule. I could also rewrite this as negative e to the negative y minus 1 to the negative 1 power, right? I can do that because exponent rules. That's the same thing as what I had before. And if I write it that way, then I have an inside function and an outside function. I could do this with the chain rule. Whichever way you decide to do it, you'll get the same answer. You could apply the quotient rule to that top part or the chain rule to the bottom part. Normally, if I were in class, I would let you tell me the way that you wanted to do it. But we're not in class, so we're going to do it the way my brain likes to do it. And my brain really prefers the chain rule. So I'm going to do the chain rule here. So if I do this with the chain rule, then I'm going to have to identify my outside function and my inside function to be able to do the derivative of my left side. because again, I'm doing the derivative of this thing on both, like taking the derivative of both sides. So we're going to start by taking the derivative on the left, and we're going to use the chain rule to do that. So I'm going to call my outside function f and my inside function g. The thing that's inside something else is this negative e to the negative y minus 1. And my outside function is x to the negative 1. That's what this thing is plugged into. So now I'm doing the chain rule. I'm going to take the derivative of my pieces. The derivative of x to the negative 1 is negative 1, x to the negative 2. And the derivative of negative e to the negative y minus 1, that's another chain rule. Okay, so to do the derivative of this, I need to do another chain rule. So my outside function, I'm going to call f. My inside function, I'm going to call g. My inside function is negative y. My outside function is e to the x. I'm not going to worry about the negative out front. It's just a coefficient that's going to come along for the ride. So now I'm going to do the chain rule. The derivative of e to the x is e to the x. The derivative of negative y is negative dy dx. And so now to finish the chain rule here, I'm going to take this and plug it in here. And so this negative comes along for the ride. The derivative of e to the negative y is this chain rule, which is e to the negative y times negative dy dx. And I'm going to subtract the derivative of 1, but the derivative of 1 is 0. So that's really not going to do anything for me. And now that we've done this chain rule inside a chain rule, I can finish the overall chain rule over here. And I'm going to get negative 1 times x, but I'm plugging my g in for my x, right? I'm plugging g into f prime. So instead of x, I'm going to write negative e to the negative y minus 1 to the negative 2. That's my f prime of g of x. And I'm going to multiply by g prime of x, which is negative e to the negative y times negative dy dx. Are you okay with this negative times a negative is going to cancel and I'm going to get a positive? So I'm not going to worry about those negatives. I'm going to write e to the negative y dy dx. That's my derivative from the chain rule on this left-hand side. And now I'm going to have that equal to the derivative of the right. The derivative of dy dx is my second derivative, so that's going to be d squared y over dx squared. And now I'm trying to find the second derivative, which is this d squared y times dx squared. That's the only one of those that I have. So really, I'm kind of done. But the weirdo thing here is that I have a dy dx here. And I don't want to leave that in here, right? I don't want to have Leibniz notation over here when I'm done. I shouldn't have that. So how do we deal with that? Let's see. Dy dx. That's my first derivative. I know what that is. We just found that. This was my first derivative, right? So I could take dy dx from here and I can plug it in there. And so if I plug that in, then my derivative, my second derivative here is going to be negative 1 times negative e to the negative y minus 1 to the negative 2 times e to the negative y times dy dx, which is negative e to the negative y minus 1 to the negative 1. And all of that is my second derivative. I'm sorry, I'm running out of space here. And notice all of these things are being multiplied. I have two things being multiplied with the same base. I could combine them. Negative 1 times negative e to the negative y minus 1 to the negative 3, because I can combine them by adding my exponents. Negative 2 minus 1 is negative 3 times e to the negative y is still here. That is my second derivative overall. Whew. So you can do repeated derivatives with implicit differentiation. Fight through any rules that you need to fight through. The weird thing when you do repeated derivatives with implicit differentiation is that you're going to get to a place where you have to plug your previous derivative answers in for that Leibniz notation. So that's something that you're going to have to do with repeated derivatives, but really only with repeated derivatives here. All right. And then one last thing before we kind of switch gears is what if I want to write the equation of the tangent line? This is something that we haven't done in a hot minute. To write the equation of the tangent line, that means I want the equation of a line. And what does the equation of a line look like? Yeah, it looks like y equals mx plus b. I want the equation of a line. So to write the equation of a line, I need two things. What two things do I need? Yep, I need a point and I need a slope. Those are the two things that you need to have to write the equation of a line. So here, I need a point. Oh, look, I want the equation of the line tangent to this function at the point 2, 1. That's the point of tangency. That's going to be the point both on my function and my tangent line. I get to use that point. I don't have to plug anything in. I'm just handed that. I love that. I love it when we just get things for free. Okay, great. So now I have the point and I just need to find the slope. How do we find the slope of the tangent line? Slope of the tangent line, that's the derivative. What we need to do is find the derivative, dy dx, evaluated at our point. So we're going to take 2, 1, we're going to plug it into dy dx. That's going to tell us the slope at 2, 1, which is the slope of the tangent line. And then we can go from there. Okay, well, before I can find the slope at 2, 1, I need to find the slope function, period. So to find the slope function, I need the derivative. I have to take the derivative of this thing. I've got x's and y's floating around everywhere. This is implicit differentiation. So we're going to do implicit differentiation. I'm going to do the derivative of the left side. We're going to do everything separated by addition, piece by piece. So to do the derivative of x times y, that's a variable times a variable. That's a product rule. Anytime you have a variable times a variable, that's a product rule. So when I'm doing the product rule there, I'm going to do the derivative of the first function, which is the derivative of x, that's 1, times the second function, y, as is, plus my first function, x, as is, times the derivative of my second function. What's the derivative of y? It's 1, but we took the derivative of y, so we have to multiply by dy dx. So all of this is the derivative of xy. And then I'm going to add to it the derivative of x squared times y squared. How do you take the derivative of x squared times y squared? Yep, that's a variable times a variable. That's another product rule. We're going to do product rule again. So we are going to do the derivative of my first function. What's the derivative of x squared? Yep, it's 2x times the second function as is. That's y squared plus my first function as is, x squared, times the derivative of my second function. What's the derivative of y squared? Yep, it's 2y, and I took the derivative of y, so I have to multiply by dy dx. All of that is the derivative of x squared plus y squared. And now I can do the derivative of my right side. What's the derivative of 6? Yep, it's 0. Okay, we did our implicit differentiation and we are in derivative land, but we have to solve for dy dx to figure out what my slope is. So here's our dy dx's. So I have a dy dx in this term and this one. So I need to put everything that with a dy dx in it on the other side. So I'm going to move this one over and I'm going to move that one over by subtracting them. So I'm going to have this left over here, which is a y, and I'm going to have this left over here. So I'm going to have y plus 2x y squared. And when I move both of these to the other side, I'm going to get negative x dy dx minus x squared times 2y times dy dx on the other side, right? Because I subtracted both of those from the other side. And now everything over here has a dy dx in it. So you're going to factor it out. And I'm not gonna lie, my brain does not like the 2 between the x squared and the y. I'm gonna move it out front because this feels way better to my brain. Hopefully y'all are okay with that. Y plus 2x y squared. And so now to get dy dx by itself, you're going to divide both sides by this. And you're going to get that y plus 2xy squared divided by negative x minus 2x squared y. That is my dy dx. That's my slope function. Okay, so am I done? No, because what I really want is the slope of my tangent line at the point 2, 1. So I need to take this derivative and I need to plug 2, 1 into it. So anywhere I see an x, I'm going to plug 2 in. Anywhere I see a y, I'm going to plug a 1 in. Go slow and get everything in the right spot. So my derivative is y, which is 1, plus 2 times x, which is 2, times y, which is 1 squared, all divided by negative x, which is 2, minus 2 times x, which is 2 squared, times y, which is 1. And now you're going to sift through this and you're going to say, okay, on top I've got 1 plus 4. That's a 5 on top. On the bottom, I have negative 2 minus 8. Negative 2 minus 8 is negative 10. So this tells me that the derivative, my slope at 2, 1 is negative 1/2. So up here, my slope, negative 1/2. That's my m. So now I have a slope and I have a point. So here is where you can rock through y equals mx plus b, and you'll plug your point and your slope in. So y, which is 1, equals m, negative 1/2, times x, which is 2, plus b. I don't know what b is, so I'm going to leave it as a b and we'll solve for it. And so I'm going to have 1 equals negative 1/2 times 2 is negative 1 plus b. So now I'm going to add that 1 to both sides and I'm going to get 2 equals b. And now I can use that and write y equals m, which is negative 1/2 times x plus b, which is 2. And that is the equation of my tangent line. It's been a minute since we did one of these, but your process is always the same when you're finding equations of tangent lines. You're going to get a point, you're going to get a slope, and you're going to plug those into y equals mx plus b. Or if you have, if you like point slope form, if you have that from previous training, you can use point slope form, which is the y minus y1 equals m times the quantity x minus x1. You can absolutely use that as well. Just make sure that you solve for y and put it in y equals mx plus b form. Okay, so that is implicit differentiation. That's how we do it. So now that we know how implicit differentiation works, we can use implicit differentiation to find derivatives of functions that we don't yet have rules for. It's going to prime the pump for getting more derivative rules, which is, I know what you really, really wanted was more derivative rules. So it's your lucky day. We're going to get several more. So implicit differentiation lets us find the derivatives of inverse trig functions. So just to remind you, inverse sine of x. This does not mean the reciprocal function of sine. This is not 1 over sine. That's cosecant. This is the inverse function of sine. So instead of plugging an angle into sine and getting the ratio of opposite over hypotenuse out, your inverse function switches that, and you put your ratio of opposite over hypotenuse into inverse sine, and what you get out is the angle. So this is what an inverse function is, right? So right now we don't have a rule for this guy, but we can use what an inverse function means, an implicit differentiation, to figure out what the derivative of this thing is. Okay, so an inverse function, y equals sine inverse of x. What this really means is that the sine of y, the sine of the angle y, is equal to the ratio x. And x represents the ratio opposite over hypotenuse, right? Whatever ratio we get out from the triangle. Okay, so I want the derivative. I want dy dx. But this is now implicitly defined. So we can use implicit differentiation, and I'm going to take the derivative of both sides. What's the derivative of sine of y? Yep, it's just the cosine y. But I took the derivative of something with a y in it, so don't forget to multiply by dy dx because implicit differentiation. And now I'm going to take the derivative of the right side. The derivative of x is 1. Okay, so now we have the derivatives of both sides. This looks nice. And we have to solve for dy dx. So to get dy dx by itself, I'm going to divide both sides by the cosine of x. And I'm going to get that dy dx is equal to 1 over the cosine of y. Oh, that's nice. That looks great. But the problem is, in my original function, I had y equals a function of x. I have my slope as a function of y, but I would really like to have the same variables down here, right, with x as my variable, rather than having y's in here. Can I do better than this? And the answer is yes. Because we have trig in our repertoire, we can actually do better than this and bring cosine of y back into terms of x. So what we're going to do is we're going to use trig, because we love trig, and we're going to make a triangle. And this says that the sine of the angle y, I'm just going to pick an angle in my triangle and call that the angle y. The sine of y, right, when I put the y into sine, the ratio that I get out of x over 1, that's the ratio of opposite over hypotenuse in this triangle. So the side opposite my angle is my opposite side, which is x. My hypotenuse, which is the longest side of the triangle, is 1. And so now I can find this side with like this side down here, a, with the Pythagorean theorem. Pythagorean theorem says that a squared plus b, which is x squared, equals 1 squared. And so I'm trying to solve for a here. So if I solve for a, I'm going to get that a squared equals 1 minus x squared. And so a is going to be the square root of 1 minus x squared. So I'm going to replace this a down here with the square root of 1 minus x squared. So now I have a full completed triangle. And so now I can actually find the cosine of y for my triangle. The cosine of y is going to be adjacent over hypotenuse. What's the length of my adjacent side? Yep, it's the square root of 1 minus x squared over my hypotenuse, which is 1. That square root divided by 1 is just itself 1 minus x squared. And so now that is what cosine of y is in terms of x's. I can just go ahead and plug that in. So my derivative, dy dx, is going to be 1 over the cosine of y. And we just found out that the cosine of y is the square root of 1 minus x squared. This is the derivative of arcsine of x with x's in it. This is my derivative. So I now have a formula for the derivative of the inverse sine function. So this is going to be my rule for the inverse sine function. To do inverse cosine function, to do the inverse cosine of x, you could rewrite it using what an inverse function means, and you could do cosine of y equals x. You would do your derivatives and you would solve everything out and come back to x, and you would find that the inverse cosine of x's derivative is negative 1 over the square root of 1 minus x squared. Notice it's the same as arcsine, it's just negative. These two are related. They're the same, just one's negative. If you did the same thing with tangent, with arctangent, you would find that the derivative of arctangent of x is 1 over x squared plus 1. And I'm going to link these two together. I'm going to jump to cotangent next, because tangent and cotangent are related, as they often are. The derivative of arccotangent of x is the same as arctangent. It's just negative. So it's going to be negative 1 over x squared plus 1. And the good news is that these are going to be related as well. The derivative of arcsecant of x is 1 over the absolute value of x times the square root of x squared minus 1. And so guess what the inverse cosecant derivative is going to be? Yep, it's negative 1 over that same absolute value of x times the square root of x squared minus 1. So I know these are ugly and complicated, but the good news is there's only 3 versions that you need to know, and you just have to remember which are connected and which are the same. And notice all of the trig functions that start with c, their derivatives are negative. So that's how you'll know which ones are positive and which ones are negative. The ones that start with c are negative, and the other ones are the positive ones. And I will say that trick of starting with c, that works for forward trig functions as well. The derivative of cosine is negative sine of x. It's negative. The derivative of cosecant of x is negative cosecant of x cotangent of x. And the derivative of cotangent of x is negative cosine squared of x. Any trig function that starts with c, its derivative is negative, which is kind of a cool, fun thing. Okay, so these are your inverse trig function derivative rules. So you're going to add these to your repertoire. You are going to have to memorize these. So I would start making flashcards to get all of your derivative rules down, because we're getting a lot of them now, and it's going to be hard to keep everything straight. So start making flashcards and working on committing these to memory. And now we're just going to hop right in, and we're going to start using these along with all of our other rules. So what if I wanted the derivative of arctangent of 3x plus 5? Okay, so if I want to take the derivative of this, notice I don't have just the arctangent of x. I have the arctangent of some stuff. I have an inside function and an outside function. I need to apply the chain rule here. So we're not going to panic. We're going to follow our form for the chain rule. And I'm going to identify an inside function and call it F, and an outside function and call it F, and an inside function and call it G. What's my inside function? Yep, it's 3x plus 5. So what's my outside function? Yep, it is the arctangent of x. And so now I'm just going to take my derivatives of each piece here. The derivative of arctangent of x, I can come up here. The derivative of arctangent of x is 1 over x squared plus 1. And the derivative of my g, the derivative of 3x plus 5 is just 3. Okay, so now I'm going to finish the chain rule and I'm going to plug that in. And so now my derivative here is going to be f prime of g of x. So 1 over, instead of x, I'm plugging g in, which is going to be 3x plus 5 squared plus 1 times g prime of x, which is 3. And there is your derivative. If your brain likes, you could put this in one fraction, right? That's like 3 over 1, and you could combine it into one fraction. And notice those 3's don't cancel. This 3 is part of something connected by addition, and it's stuck in squared jail, so they're not free to cancel. This is the best we got. All right, so I want you to go ahead, pause the video, and see if you can do dy dx evaluated at x equals 0 for the function y equals the inverse cosecant of e to the x plus 1. Go ahead, pause the video. I want you to give this a go, and when you're ready, go ahead and hit play. All right, hopefully you have started to work on this. Now, to do the derivative of arc cosecant of e to the x plus 1, hopefully you identified that you have stuff inside an inverse cosecant. This is not just an x inside here, it's stuff, which means you need to apply, yep, the chain rule. Sorry, my pen stopped working there for a second. There we go. We're going to apply the chain rule. And so you're going to do your outside function and call it f. You're going to do your inside function and call it g. Your inside function should be e to the x plus 1. Your outside function will be the inverse cosecant of x. And now we'll just do our derivatives of each piece. The derivative of arc cosecant, this is one of the extra nasty ones, which is this guy. -1 over the absolute value of x. It's -1 over the absolute value of x times the square root of x squared minus 1. And the derivative of e to the x plus 1 is just e to the x, because the derivative of 1 is 0. And so now you will finish your chain rule. And so the derivative of the function that we had here is going to be -1 over the absolute value of x, but instead of x, I'm going to plug g in, and I'm going to get e to the x plus 1 times the square root of x. But I don't just have an x, I'm going to plug g in for it. So I'm going to have e to the x plus 1 squared minus 1. That is f prime of g of x. And I have to multiply by g prime of x, which is e to the x. And then we're not quite done. We were asked to plug in x equals 0. So I'm not going to worry about doing any simplification. I'm just going to plug in x equals 0. And I'm going to get -1 over the absolute value of e to the 0 plus 1 times the square root of e to the 0 plus 1 squared minus 1. I'm going to take all of that and multiply by e to the 0. All right. What's e to the 0? Yep, anything to the 0 power is 1. So all of those e to the 0s are just going to be 1s. And so I'm going to have -1 over the absolute value of 2 times the square root of 2 squared minus 1. And again, times 1, that's not going to do anything. So I'm just going to ignore that one times 1 on the back. And so I'm going to have -1 over the absolute value of 2 is just 2 times the square root of 4 minus 1 is 3. And again, you do not have to rationalize for me or for achieve. We are both very happy with -1 over 2 root 3. Okay, so those are your inverse trig functions, and those are going to wrap up section 3.8. So that is section 3.8. We're going to start section 3.9, and we're just going to get a few more derivative rules. So the bad news is that we're getting more derivative rules. The good news is that these are your last derivative rules that we're going to have to cover. So without further ado, that's not the one I want. I want to come back here. Let's get into section 3.9. Here we go. So now we're going to get into derivatives of exponential and log functions. Now you already have an exponential derivative rule in your repertoire, right? You know e to the x. E to the x is an exponential function. What's the derivative of e to the x? It's e to the x. So now we are going to say, what if I don't have e to the x? What if I have 5 to the x? And we're going to figure out how to do that derivative. We're also going to say, what if I have logarithms? Because logs and exponentials are tied together. They're inverse functions. And so we're going to be able to do the derivatives of logs as well. So let's start with y equals ln x. All right, so to find a derivative rule for this, we are going to start by rewriting this in exponential form. There we go. And then we are going to use implicit differentiation to find our derivative. So ln is log base e of x, right? It's a logarithm and it's got base e. I'm going to take this logarithmic notation and I'm going to rewrite it in exponential notation. So if you remember this from college algebra or pre-calculus, you're going to rewrite this. The base of the log becomes the base of an exponential on the other side. And this really means that e to the y is equal to x. That's really what y equals ln x means. It means that e to the y is equal to x. Okay, so now that I have it written in this form, those are things that I can take derivatives of. So let's go ahead and take the derivatives using implicit differentiation. So what's the derivative of e to the y? The derivative of e to the y is e to the y. And I took the derivative of something with a y in it. So we're going to multiply by that dy dx from implicit differentiation. And we got to take the derivative of the other side. What's the derivative of x? Yep, it's 1. And we're going to solve for dy dx, which is right here. And so to get dy dx by itself, I'm going to divide both sides by that e to the y. And I have dy dx. But again, dy dx says that my variable should be x. I would really love to be able to write this with x's in it instead of y's. But hang on. I know what y is. Y is ln x. So I can go ahead and plug that in. And I've got 1 over e to the y is ln x. And e to the ln of x. This simplifies. This is 1 over e times log base e of x. When the base of the exponential and the base of the log are the same, they cancel each other out. This is just 1 over x. That, my friends, is the derivative of ln x. The derivative of the natural log of x is just 1 over x. So let's practice this. We've got this. So now we're going to add this to our repertoire, and we're going to find the derivative of each of these functions. All right, I've got the natural log of 5x plus 4. I don't know what the derivative of this is. I know the derivative of ln x, but this isn't just an x. This is stuff, which means this is a chain rule. We're going to have to apply a chain rule to this. I've got stuff. All right, I still can't write chain. We're full circle here from the beginning. Still can't write chain. At least I'm consistent, I guess. Okay, so to do the chain rule, we're going to identify my outside function and call it f. We're going to identify my inside function and call it g. My inside function here is 5x plus 4. My outside function is ln x. And now I can take the derivatives of each of those pieces. What's the derivative of ln x? We just got this one. That's 1 over x. That's our new one. And the derivative of my inside function, what's the derivative of 5x plus 4? Yep, it's just 5. And we are going to finish the chain rule. We're going to plug g into f prime. So the derivative of my whole big f prime, right, the derivative of this one. Sorry that we have multiple f's flying around. But the derivative of my main f of x function is going to be 1 over x. But I'm plugging g in for that x. So I'm going to have 1 over 5x plus 4 times g prime of x, which is 5. If your brain likes, you can put that 5 over the 5x plus 4. And do not cancel those 5s. This one on the bottom is not free to cancel. It's part of something that's connected by addition, so it's not free to cancel. This is the best that we can do. So you're going to put a box around it, and that is my derivative. All right, number 2. How do we take the derivative of x times the ln of x? Well, I've got x, something with a variable, times the ln of x, something with a variable. This is a product rule. Okay. Deep breath. We're not going to overthink it. We know how the product rule works. So we're going to do the derivative of my first function. The first function here is x. My second function is ln x. So the derivative of my first function, what's the derivative of x? 1 times the second function as is, that's ln of x as is, plus the first function as is, which is just x, times the derivative of my second function. What's the derivative of ln x? Yep, it's 1 over x. And so to simplify this, 1 times ln x is just ln x. X times 1 over x is just 1 because those x's cancel. And this is my derivative. All right, next one. I need to find the derivative of ln x squared. Well, depending on how you look at it, there's a couple of different ways that you can do it. The way that it's currently written, you've got an inside function, ln x, and an outside function, x squared. You can do the chain rule on that. Or you could look at this as being ln x times ln x. That is two functions with variables being multiplied. That would be a product rule. You can go where your brain likes. We could either do a chain rule or a product rule here. We've been doing a lot of chain rules, so I'm actually going to do the product rule this time. So if your brain still likes the chain rule, go ahead and do the chain rule. You'll get the same thing either way. So if I decide to do a product rule, then this is my first function. This is my second function. So the overall f prime of x, right, the derivative of this guy, my original function, is going to be the derivative of my first function. What's the derivative of ln x? Yep, it's 1 over x times the second function, ln x as is, plus the first function as is, ln x. I don't know why sometimes I use parentheses and sometimes I don't. Sorry about that if that's confusing. Times the derivative of the second function. What's the derivative of ln x? Yep, it's 1 over x. So notice what I have here is ln x over x plus another ln x over x. When I combine those, I get 2 ln x's over x. And that is my derivative. If you did the chain rule, you would get the same thing. We've got stuff squared. The derivative of stuff squared is 2 times your stuff. So that would be 2 times the ln of x times the derivative of your stuff, which would be 1 over x. And you would get 2 ln x times 1 over x, and you would get exactly the same function. All right, one more, and then we'll get our last derivative rules of this, of really the term, I think, which is good news. Okay, how am I going to do the derivative of this guy? ln of sine x. Okay, well, I've got the ln of a whole bunch of stuff. This is definitely going to, I've got inside and outside functions here, right? So this is definitely going to be a chain rule. So I'm not going to panic. I'm going to find my outside function and call it f. I'm going to find my inside function and call it g. What's my inside function? I'm going to call all of this my inside function so that my outside function is just that outer ln. So my inside function here is the ln of sine x. And that means my outside function here is that ln x, which is this one. Okay, I have my inside and outside function. So now I'm just going to rock through the chain rule and I'm going to do my derivatives. The derivative of ln x is 1 over x. We've got that one. Now, the derivative of ln of sine x. That's the ln of some stuff again. This is another chain rule. Okay, so we've got a chain rule inside a chain rule. We are not going to panic. We are going to identify my outer function and call it f. I'm going to identify my inner function and call it g. What function is inside another function in here? Yep, my inside function is sine x. My outside function is ln x. And then I'm going to take the derivative of each of my pieces. Derivative of ln x is 1 over x. We just did that. What's the derivative of sine x? Yep, it's cosine x. And now I'm going to finish the chain rule. I'm going to plug g into f prime, and I'm going to get 1 over sine x. That's my f prime of g of x times g prime of x, which is my cosine of x. Whew. Okay, so that completes the chain rule inside my chain rule. And now I need to come back out and I need to finish this outer one. And so now I can do my f prime of g out here. So the derivative of this whole big original function is going to be f prime of g of x. It's going to be 1 g in here. Instead of x, it's going to be ln sine x. Times g prime of x, which is this. I'm going to write that as cosine of x over sine x because my brain likes that better. I'm just going to put it into a single fraction. And that's my derivative. If you really want to, you could put this all into one function, cosine x over ln. I'm going to put the sine of x in front so I know what's inside where. Sine x. I guess we could simplify it a little bit, actually. So actually, before I do that, because we could actually make this a little bit better. Instead of two trig functions, we could write this in terms of just one, right? Cosine over sine. That's just cotangent, right? Cosine divided by sine, that's cotangent of x. And so I can just write this with fewer terms. So this would be cotangent of x divided by the natural log of sine x. I think that's about as simple as we could go. It's a little simpler just because we have one less trig function. So I'll call that simplified. All right, y'all. 2 more rules. What if we have bases other than e? So what if I have log base b of x, right? So that might look like log base 7 of x, right? What if I have a different number down there? What if instead of y equals e to the x, what if I have like y equals 5 to the x, right? I've got a different base than e. How do I take the derivative of these guys? Well, in order to do that, we're going to start with log base b of x. And we are going to turn log base b of x into things with ln's using our change of base formula. The change of base formula is something that you have seen in college algebra and pre-calculus. It might have been a little bit. But like if I were to put log base 7 of 2 into my calculator, I don't have a log base 7 button. So we had to use the change of base formula to do that. Change of base formula says you can either use log base 10 or log base e. We're going to use log base e here because I have a derivative rule for that. And so log base b of x can be written as the natural log of x, the thing inside my log, divided by the ln of my base b. And so our variable here is x. B is just a number. And the ln of b is also just a number. And so I could write this as 1 over ln of b as being a coefficient. And I'm going to multiply that by ln x, which is something with a variable in it. And so if I write my change of base this way, then to take the derivative of it, dy dx is going to be, this is a constant, or sorry, this is a coefficient, so it's going to come along for the ride, 1 over ln b, it's just a number, times the derivative of ln x, which is 1 over x. This is the derivative of log base b of x. Typically, we write it in one fraction, and we put the x first, so it's going to be 1 over x times the natural log of your base. That's my derivative rule for log base b of x. So for instance, what if I wanted to do the derivative of that log base 7 of x that I had up there? What's the derivative of log base 7 of x? Well, this says it's going to be 1 over x, and then down here in the denominator with x, I'm going to multiply by the ln of my base, which is 7. So that's what the derivative of log base 7 of x looks like. That's not too terrible. Okay, so now what if I have an exponential with a base other than e? Okay, so if I have y equals b to the x, now that I know how to take the derivative of log base b of x, I'm going to rewrite this in logarithmic form, and I'm going to write this as log base b of y equals x. That's the equivalent logarithmic form. And now I can take the derivative of both sides. And implicitly, what's the derivative of log base b of y? Well, it's going to be 1 over y times the ln of b, right, using the formula we just got. And we took the derivative of something with a y in it, so we're going to multiply by dy dx because implicit. And then on the other side, what's the derivative of x? Yep, it's 1. And now to finish the implicit differentiation, I need to solve for dy dx here. So to do that, I'm going to multiply both sides by y and multiply both sides by the ln of b. And so notice that what we get here is that dy dx over there is going to be equal to the ln of b times y. But again, I want x's. My variable should be x, not y. So I'm going to come back here and I'm going to say, oh, y is b to the x. So I'm going to go ahead and say this is ln of b times b to the x. And this is our last derivative rule that we have. The derivative of b to the x is itself b to the x times the natural log of the base. We usually write it in this order. That's just kind of the way I wrote it when I was solving, but this is the order that we usually see it in. The derivative of e to the x is e to the x. The derivative of any other base to the x is itself that base to the x times the ln of your base. So with that in mind, what is the derivative of 5 to the x? Yep, it is 5 to the x times the natural log of your base, which is 5. It's 5 to the x times the ln of 5. All right. We're going to do these 2 problems, and then we are going to be done for the day. So how would I take the derivative of 4 to the 3x power? Well, I know how to take the derivative of 4 to the x now, right, because of this guy. But I have a 3x, not just an x. So the fact that I have more stuff up there says this is 4 to the stuff. This is a chain rule. And so we're going to do the chain rule. We know what we're doing now, outside and inside. My inside function, the thing that's inside, is 3x. And the function that it is inside of is 4 to the x power. Right, that's my inside and outside function. If I plug g into f, I get 4 to the 3x, which is my original, so I feel good. And now we can rock through and take the derivative of my pieces. The derivative of 4 to the x. We just learned this. It's 4 to the x times the ln of 4. And then the derivative of 3x is just 3. So we can do our chain rule. We'll plug 3x, our g, into f prime. So overall, the derivative of my main function here is f prime of g. So it's going to be 4 to the, instead of x, it's going to be 3x times the ln of 4. That's my f prime of g of x times g prime of x, which is just 3. There's nothing here to combine. You can reorganize and put your numbers in front if you want, or you can just leave it like that. And that is the derivative of 4 to the 3x. All right, how are we going to do the derivative of y equals log base 2 of x squared plus 1? Well, I know how to do the derivative of log base 2 of x, right? We just got that one. But I don't know how to do log base 2 of x squared plus 1. This is log base 2 of some stuff. That's a chain rule. So we're going to do the chain rule. You should be comfortable with this by now. We're going to find our inside function. Which function is inside something else? Yep, it's x squared plus 1. What's our outside function? That's inside of log base 2 of x. so now we can do our derivatives. What's the derivative of log base 2 of x? This is the one we just got. Log base 2 of x is going to be 1 over x. And down here in the denominator with x, I'm going to multiply by the ln of my base, which is the ln of 2. And then g prime, the derivative of x squared plus 1, that is 2x. And now we'll finish our chain rule. So the derivative of my original function here is going to be f prime of g. So I'm going to do 1 over, instead of x, I have x squared plus 1. And then I have the ln of 2. That's just a number. That's my f prime of g of x times g prime of x, which is 2x. You can combine that into a single fraction if you want. That's 2x over 1. So this can be written as 2x over x squared plus 1 times the ln of 2. And these x's can't cancel. This is connected by addition, so that ruins any canceling. And we are done. Oh, and we can't cancel the 2's. This 2 is stuck in ln jail, so I can't cancel those either. Okay. Those are the end of your derivative rules. That is as far as we're going to get in section 3.9 right now. We will finish section 3.9. We only have one more topic here. We should finish that fairly quickly at the beginning of Tuesday. And then bring any questions that you have for anything that we've covered thus far. And we'll get yourselves ready for exam 2. So 3.7 and 3.8 will be due on Monday. That is September 30th at midnight. And 3.9 will be due on Wednesday. That is October 2nd at midnight. Stay safe out there with Helene coming through, and I will see you next week.